Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, our next session is shared by Sham Kakade. He is a machine learning researcher in our lab.
Yeah, so as Peter Lee and others mentioned, there's really been tremendous excitement and progress in machine learning, and our next session is going to bring together a number of interesting researchers who are looking at some of the challenges we're going to face in machine learning, and many of these challenges at their core might not even be machine learning questions. So to start us off, we have Antonio Torralba, who's really been doing a lot of very thought-provoking work on, you might think it's just visual perception is a lot of his work.
Thank you. So I have 12 minutes, 50 slides, and a strong Spanish accent. So what can go wrong here? Okay, so this is a really exciting time for computer vision. There are lots of different applications you can find that use vision to sell products like Kinect or digital cameras. Now you can have face detection, and it works really, really well. So people get really excited, and new students come into the field. And I want to give you a sense of what is the first experiences of a student that starts doing computer vision. So it sees that there are lots of different models for object recognition, and it says, oh, wow, I want to start. So it downloads some code, compiles, it doesn't work, then it compiles again, it works. Then it picks a data set, and it says, OK, I'm going to train my object detection system to detect something. And then it takes an image, it runs the detector, and it says car. OK, so who is to blame here? Is the student incompetent, or maybe there is a car there? So who is to blame here? And there are a number of things that go into place in order to make all the systems work. There is the representation, the features, the training set that you use, the machine learning algorithms that you use. So we are going to look one by one on who is to blame in this failure. Or maybe it's just the student to blame. So how it works, object detection. So let's look at the representation first. The most successful systems for object detection, what they do is what we call the bounding box. They take an image. Let's say that you're looking for faces. You take a box out of this picture, and you ask the question, is this a face, yes or not? And in order to do that, you extract some descriptors from here, and then you apply just a function that will just look at this box. And then if the face is not there, you just move one pixel, and you ask the same question, and then one more pixel, and one more pixel, until you cover the entire picture. And if you don't even find the face, it's not because the face is not there. Maybe you just got the scale wrong. So you try a different size, and you keep doing this over and over again. So this is very different from how humans do object detection. So just to illustrate that, let's look at this video. This is a very low resolution video, and you can still tell everything that is going on here. This is about 20 pixels worth of vertical information. So if you were just to look at small boxes here, you wouldn't be able to tell anything. And yet you can recognize everything that goes on. So this is just a normal day in my office when I was a postdoc. This was my colleague, Rob Fergus. And so how are you able to recognize all these things? Well, because you actually don't just look at boxes. You put everything in correspondence, and you do scene reasoning. And in fact, when you look at this video, you are putting into the interpretation a lot more than there is inside. So let's look at the high-resolution video. Here it is. So you can see, that there are a few things. This is the type of things that we were doing in the office. He doesn't really listen to music. Anyway, I think there is some progress in mouses recently. Anyway, so the representation is wrong, and there is a lot of research trying to resolve that, so I'm not going to go there. But let's move to the next thing, the features. The features. So why is that we get this car here? OK, what is that the detector sees? If you look at that, this is the patch. This is what the detector is going to see, just this piece of the image. And what you do is you will apply to that patch some descriptors. And there are lots of different descriptors that exist in the computer vision community. Here I just show a few of them. You can see they have 4 letters, 3 letters. There are all kinds of acronyms. So the most popular one right now is HAWK. And HAWK is something, that extracts some orientations, edges, and it applies some kind of complicated nonlinearity to the picture. So this is the recipe to compute Hawk. You take the image, you do a bunch of stuff, and then at the end you get a vector for each window that will tell you something about that window. So how do we know what the detector actually sees? This is the typical visualization that people will use to try to get a sense of what this descriptor sees on the picture. You have this picture, and well, you don't really, there are a lot of nonlinearities, so people generally show things like this, and what they are showing is at each location what is the dominant orientation. This is actually a representation of all the numbers that there are on the Hawk descriptor. It's just not very clear what is going on here. So two of the students in my lab, Carl and Aditya, they were really working on this, and they wondered, okay, what is that this detector actually gets to see on this picture? So what they tried was to see if you could take this and actually try to recover the input image. So it's a very nonlinear problem, so it's not easy to do, but they worked really hard, and at the end, they got something out. And this is what they got back. So you can see that it's a nice bottle. No? It actually looks like the bottle. And it also reveals some of the things that the descriptor is doing. Like, you can see that there is almost no contrast in this part of the picture, but in the reconstruction, you can see the back of the bottle, showing that this descriptor is actually doing contrast normalization, all kinds of things that we know are very important for recognition. But what is else going on? Maybe there are some advantages, but maybe there is something lost in this process, and we don't know what it is. So what they did was to take the detector, a detector trained to recognize objects based on this descriptor, and they run it on images, and they picked then all the places where the detector had high confidence that the object that they were looking for was there. So what I'm showing here are the dispatches of the images where the detector fired, and then I'm showing the reconstruction of those descriptors. So you can see here there are a mixture of things that are right and wrong, and can you tell which things are actually wrong? It's pretty hard, huh? Any guesses? Which one is a false alarm? The detector thought the object is there, but it's not there. They are all wrong. These are all false alarms. But when you look at them, they look very natural. You can even make stories about them. No? Like here, there is somebody looking into a mirror and somebody walking. And you can tell stories about all these objects. And people agree about those things. But they are all wrong. So it's just nuts. So here is what is going on now. We can go back to our original picture where the students say, OK, this is not working. You can look at the patch. And there is no reason why this should fail. Why is there a car there? You can look what scientists normally see. This is what they see. So still, you are totally clueless. But if you look at what the feature actually sees, this is what it sees. And it actually looks like a car. So the algorithm is working. There is a car there. And the funny thing is that you can actually look at the performances that people will get in guessing the presence or absence of an object by looking at these reconstructions. And you can see that the performance that they achieve is basically the same performances that the best classifier you can put than a classifier that you can put on the descriptors themselves. I mean, this is just some curves showing something, and the red is humans, this is the classifier, and they are just doing slightly better by looking at the reconstructions. So there is not a lot of room of improvement that you can achieve by improving the detector. Maybe you can just bridge this gap, but there is really not a lot you can do. So the features are to blame in this case. So what else is to blame? Well, there is another arbitrary choice, which is the training set. Which images do you use to train your algorithm? And there is a lot of effort nowadays in computer vision to try to build really big databases of images that you can use to train algorithms and to evaluate them. And there are two things that you need to do. You need to collect images, and you need to label them. You need to put ground truth to them. So how do you collect images? There are many different ways, and each way has its own problems. One of the most popular ones is to go to the web and collect images by Googling them or something. So let's say that you're looking for mugs. You go to Google, you query for mug, and this is what you get. And you can see this is not a random set of mugs. They all have the handle on the right, besides maybe 3 that have the handle on the left. So why is that? I mean, this is not an unbiased set. Or you can go and look for bedrooms, and these are the pictures that you get back. And this is not a random set of bedrooms. For first, the bed is always present in the picture. OK, that's fine. But look at the bed. how organized it is, how clean. I mean, this is not a random set of beds. You can look for a student bedroom, and you get still this. And we know student bedrooms are not like this, okay? This is not how my bedroom looks like. Of course, I wouldn't post any picture of my bedroom on the web. This is the kind of thing that we look for. This is a real student bedroom. Okay, so that's one thing. And the other thing is image annotation. We need to get the images labeled. And one very popular way of doing it is by crowdsourcing. Crowdsourcing is now a very useful tool if you want to build a very big database. And there are a number of crowdsourcing tools for image annotation. Like one is LabelMe, which we created in 2005, that allows people to go to the web, and there is an annotation tool, like to trace the boundary of objects, and that gives us information about all the objects that we can label that are present on the picture. And there is also Amazon Mechanical Turk, which is this very popular website that you can post small tasks, and people will do them for 1 cent or something like that. And it's very useful in computer vision. A lot of people are using them. But the question is, when you put all these tasks on the web, who is actually doing the work? Because there is a lot of random people going there. And if you look at the plots of how many tasks do each worker, if you do something like this, so these plots are ranking workers by the amount of work that they do. So the vertical axis is the amount of tasks completed by each worker, and this is rank order in this list. You get to see always these power laws. This happens in Amazon Mechanical Turk, and also in LabelMe. You get to see the same distributions, very robust. So it's like there is one guy here that really is doing all the work, and then all the others just having a little bit of fun, and they're moving into something else. So my suggestion is, let's just hire that guy there. So I have no idea who is in Amazon Mechanical Turk, but I know who is on LabelMe, and that's my mother. My mother has labeled a lot of things. So here is a random worker on Amazon Mechanical Turk labeling an image. There are some things that are useful, but there is a lot of noise. And this is my mother. Okay, she really does beautiful work. Look, all the objects labeled, the things in the back. It's just beautiful. Here you take this image, you put it on Amazon Mechanical Turk, and somebody will say, well, binders. My mother goes one by one, label them on. Of course, there are a few things that she refuses to label, like this in here. Anyway, she has labeled a lot of things, and just to put my mother's work in context, let's look at some of the most famous databases out there, like Pascal, which is a very important database in computer vision. The way it's been labeled is you take 10 graduate students, you close them in a room, and you say, you cannot get out of here until you have labeled all these images. It's a very successful strategy. So they have been working for about 10 days or so, and they got labels about 28,000 bounding boxes. So this is given an image, you put a rectangle on top of the object, and you say what the object is. Then ImageNet, another very famous database, this has been labeled with Amazon Mechanical Turk. They have more than 25,000 workers going on here, and most of the annotations are single images with one word saying if the object is present there or not. And this is my mother. My mother has labeled more than a quarter million of objects, but this is not just putting one word or a bounding box. This is a full segmentation. Look at all the clicks here. If you count the number of clicks, this is comparable to about 10,000 Amazon Mechanical Turkers. So she's done a lot of work. So I'm looking for more parents, if you have any, that are. Anyway, the conclusions is, who is to blame about all these things? Well, actually everybody. There is a lot of progress that needs to be made still. It's a really exciting time for computer vision. There are lots of things to do, but fortunately, we still have a lot of work to do. Otherwise, I'm out of business. And
so is your mother.
And my mother, yeah. So I'm not talking about the learning algorithm. That's for the machine learning people to do. So thank you for your attention.
Time for a few questions while we switch. Where's your mother live?
Yes, where my mother lives. She lives in Palma de Mallorca, in the Balearic Islands. So she has better things to do than labeling images. Yes? Oh, if somebody has studied? Oh, I see. If it helps to get your brain better, I guess. No, I don't know if anybody has studied that, but my mother is learning English pretty fast. So I guess it's helping my mother in some sense. Yeah. She was playing a lot of solitary, so I thought that she could do this.
Yeah. Oh, no, 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 no.
Evaluating the algorithm in terms of the ability of your students to visualize the output of the algorithm. All goes in there.
Okay, so in short, the question is if there is a way of defining a good gold standard for object detection, and if you inject in the training set more variability of different viewpoints of max, if performances get better. That's the summary of the question. And well, the problem is also the test set. If the test set, generally these data sets are done for both training and evaluating the performances. And if your training set has a lot of richness and so on, but then you're testing it on a poor benchmark, then you might actually get hurt by learning from a too generic data set. But the ideal thing will be to have also a test set that is very, very, very generic, and it's just very hard to. Sorry?
Well, maybe we should continue the discussion afterwards.
Yeah, we can talk later. It's a complicated problem, but I agree with you.
So our next speaker is Hannah Wallach. Hannah has had an interesting trajectory in that she started as a machine learning person and become an expert in the area, and has now been addressing a lot of social science questions with these different techniques. So, Hannah?
All right, great. Hi, everyone. I want to start by saying that my mother is not so detail-oriented. In fact, she has recently joined a contemporary interpretive dance troupe for the elderly. And I feel like my talk is therefore more in that style than perhaps some of the more mathematically oriented things today. Anyhow, with that out of the way, I'm Hannah. I'm a professor at UMass Amherst. And I'm also a member of UMass's interdisciplinary computational social science research initiative. So as Shyam said, my background is in machine learning. And I spent my 20s developing all kinds of very technical algorithms for all kinds of things. But more recently, I've been working on machine learning methods for analyzing complex social processes. That said, I'm not actually going to be talking about my specific research questions today. Instead, what I'm going to be doing is I'm going to be talking about 4 challenges intended as talking points that I think really lie at the heart of computational social science research. The first of these challenges, Jeanette Wing actually stole my thunder on this one, so you've kind of heard a bit of that already. And it's really intended for everyone working in this area of computational social science. The last 3 are sort of more oriented at machine learning researchers and computer scientists. So computational social science is inherently interdisciplinary. And in order to make truly groundbreaking advances, collaboration is absolutely necessary. Social scientists provide all kinds of important context into the most pertinent research questions, data sources, acquisition methods, and things like that, while computer scientists and statisticians provide significant expertise in developing new mathematical models and computational tools. When I first started working in this area, I felt as if there was maybe a disconnect between the research done by computer scientists and the research done by social scientists. And I kept overhearing conversations between people from these 2 groups that involved the sentence, "I don't get it, why is that a research question?" So I'm just going to launch right in with my first challenge, which is establishing a common language for interdisciplinary communication. In order to establish productive collaborations between researchers with really disparate backgrounds, it's absolutely imperative that those researchers understand each other's cultural norms, each other's values, each other's research goals, and each other's methodological frameworks. And this might sound simple, but in fact it's a really non-trivial task. People train for years in order to understand their chosen discipline and its culture and values, and so there's no reason why we should be able to launch in and immediately understand those things from another discipline overnight. So as a result, I think it's really important that researchers in computational social science really work on creating a common language by listening and talking to one another, by participating in research institutes such as Microsoft Research here in New England, but also seeking out informal conversations, interdisciplinary workshops, seminar series, and even publication venues. So establishing a common language is really especially important when the objects of study are as widespread and diverse as complex social processes. Sure, informal collaborations and conversations between friends or colleagues are social processes, but so are the activities of entire corporations or entire government organizations. So as an example, consider the US patent system. This is actually the patent for the glass staircase in every single Apple store. Why not? So the US patent system aims to promote industrial and technological progress, to strengthen the economy, to protect intellectual property, and so on. And there are a whole range of people involved in achieving these aims. You've got inventors, you've got assignees, you've got patent examiners, patent attorneys, each of whom have differing goals. And in some cases, their goals might even be explicitly contradictory. So patent attorneys want to make sure that their clients' aims are as expansive as possible, while part of a patent examiner's job is to make sure that claims are not overly expansive. And there are a ton of different types of information arising in this entire complex social process and all these interactions. As you can kind of see from this, you have things like dates, you have addresses, you have categories, you have names and related literature, related patents, as well as the text of the patents themselves, parts of which are written in scientific language and parts of which are written in legal language and intended deliberately to be obfuscatory. So what, if anything, do complex social processes have in common? Well, they all consist of individuals or groups of individuals interacting in order to achieve specific and sometimes contradictory goals. But there's more than just that. They all possess three common characteristics. The first of which is structure, who's interacting with whom. The second of which is associated content. In other words, information used in or arising from these interactions. And this might include categories or financial data and other kinds of numerical data, but it can also include text and documents and informal communications written by people to interact with other people, not written for researchers to study. And finally, most social processes exhibit dynamics of some sort. Their structure or content, or both, can change over time or space. And these changes can be gradual or sudden, and either permanent or transient. And this brings me to my second challenge, developing models that simultaneously capture multiple modalities of the same process, moving beyond static snapshots of interaction structure, models of low-dimensional metadata, and other kinds of simple temporal changes. In order to build accurate models of complex social processes, we need to capture their nuanced, multifaceted nature. And this is where kind of rich textual content and complex temporal or spatial dynamics can really reveal important latent information that is crucial to reasoning about those complex social processes. Furthermore, these three things, structure, content, and dynamics, are not independent. And so it's really necessary to build integrated joint models. So one of the biggest areas of disconnect between computer scientists and social scientists is the end goal of any research project. And this disconnect is nicely summarized in this quote by Gary King and Dan Hopkins. And I'm going to read it to you. Policymakers, or computer scientists, might be interested in finding the needle in the haystack, such as a potential terrorist threat or the right web page to display from a search. But social scientists are more commonly interested in characterizing the haystack. Since reading this quote, I've done a bunch of thinking about the different types of modeling tasks undertaken by computer scientists and social scientists, and I think they fall into 3 categories. The first is prediction, and in general, it's computer scientists or decision makers who are most interested in predictive tasks. That said, there's increasing interest from social scientists because you can use predictive tasks, even if they're not directly related to your end goal, to validate models that will be subsequently used for something else. The second is explanation. So here the focus is on why questions. In other words, finding plausible or probable explanations for the observed data. And in general, it's social scientists who are most usually interested in explanatory tasks. And finally, the third is exploration. So exploration is all about uncovering patterns in data, usually patterns that we don't already know about. And modeling tasks that fall into this category are also kind of characterizing the haystack tasks. Although contrary to the quote by King and Hopkins, both computer scientists and social scientists are interested in exploration, though interestingly, neither one quite prioritizes it as a first-order modeling task. So my third challenge, and this is specifically for machine learning researchers really, is therefore developing models that are not just black box prediction engines, but instead facilitate explanatory and exploratory analyses, as well as predictive analyses. And in order to do this, such models really need to encode modeling assumptions so that conclusions can be drawn in an appropriate context. They need to represent and maintain uncertainty, and they need to have interpretable model structure. And the framework of hierarchical Bayesian latent variable modeling is particularly well suited to these kinds of tasks. So my final challenge is a little controversial, given the title of this panel that's kind of focusing on big data. But nonetheless, I think it's really important. I just spent a week at a conference in the UK discussing these issues with a bunch of social scientists, so I wanted to bring it up. Within computer science, there's a ton of enthusiasm for big data at the moment. And this is totally unsurprising and completely reasonable. We finally have the kind of computational infrastructure that supports the analysis of really massive data sets. And this brings up some really exciting computational challenges. But here's the thing. Many social scientists, especially social scientists in academia, don't have big data, or at least not big data in the way computer scientists usually think about it. Sometimes this is because they're trying to answer questions for which big data just doesn't exist. For example, consider political scientists trying to look at the US Supreme Court opinions. That's the opinions of 9 people. You're just not going to get 10,000 people there. As another example, sometimes social scientists have many different small data sets, which each one has like a different emphasis, but when combined, they reveal a complete picture of the or more complete picture of the underlying social process. So here, consider, for example, publications and patents arising from a same institution. Publications are useful, patents are useful, but when you combine them together, and look at differences in kind of language usage and stuff like that, you actually get a much more complete picture of technological innovation from that particular institution. And then some social scientists have longitudinal data. So data collected regarding a small number of entities over a long period of time at different intervals. And again, that's something that needs to be considered. And then finally, my favorite, many social scientists work with what I call artisanal data. So these are data sets that have been carefully selected, hand-labeled, or curated in some other way by a group of experts for some specific purpose. And it's really, really important that in our enthusiasm for big data, we don't forget about those as well. So challenge number 4 is really this. Develop models for composite, longitudinal, artisanal, and small data, as well as models for big data. And with that, I'm going to stop because I'm over time, but computational social science is awesome, and MSR is doing really great work in this area. That's it. Okay. Yes. Right, exactly. Okay, so Okay, sorry. The question was, could you give an example of an artisanal data set? So one example there, this kind of came up last week because I was talking to some political scientists who were analyzing differences in opinion of politicians in the primaries versus the general election. So how people kind of change their opinions and go back on stuff that they said previously. And the particular data set that they were looking at, they had political scientists sit down and hand annotate certain opinions and whether subsequent opinions contradicted them and stuff like that. So that's the kind of thing that I'm thinking about there.
I thought of big data as including all kinds of data.
Yeah.
So I don't quite understand the point
Sure.
that you made in that fourth point. Why wouldn't he be interested in all data?
Okay. So here's the thing. I think there's this tendency. So here's what the issue is. I think with a large data set, it can sometimes be relatively easy to learn about coarse-grained things from that data. You know, you can look at a massive data set and draw these very coarse-grained conclusions about a large population of people and stuff like that. But when working with a much smaller, and you can do that using a pretty simple model or pretty standard statistical techniques. I think when you're working with a much smaller data set, you still want to be able to extract signal from noise, but often that signal is much finer grained.
My impression is, as an outsider,
Sure.
is what machine learning has always done, had a tiny number of data sets, and that's its whole history. And the big data is new things.
So I don't know if that's quite true. Here's why. So I've been doing a lot of work with social scientists who might have only 100 documents that they want to apply machine learning and natural language techniques to. You're right that machine learning and natural language techniques were often, you know, pioneered for small-ish data sets, but we're still talking on the order of thousands, not 100 or 50. And so I'm really interested in sort of thinking about some of the challenges that arise when you do have a data set that is small enough for a single human to sit down and look at, but there might be things in that data set that a human with their own particular biases and background might miss.
So why don't we change speakers now? So our next speaker, are you up and running? Yes, our next speaker is David Rothschild. David is an applied economist who has been looking at a lot of interesting forecasting problems. He's now at our sister lab in New York.
Thank you. And I'd like to start out, and I think I can speak for everyone in New York, thanking Jennifer and Christian for us being here today. They opened up the New York lab a little over a year ago, and we're just thrilled to be here and be a part of this community. And today I'm going to talk about polling lay people, and it's going to be a little bit about forecasting and indicators. This here is what we had up as our indication for what was going to happen in the 2012 election in February of 2012. We did pretty well. These are probabilities, and the darker reds meant they're very likely for Romney, and the darker blues very likely for Obama. And Florida we were a little off on, but we had that pink anyways. And this comes from data that we pulled. A lot of it was from fundamental data. These are kind of things about past election results and who is incumbent and economic indicators. And during the course of an election cycle, we kind of change over to other types of data, polls, prediction markets, social media data. And what I'm going to talk about today is kind of how that's going to be changing in the near future and what we're doing about it. Because maps like these, in some ways, are going to get easier to make. In some ways, they're going to get harder to make. And what I want to keep in mind as I talk today are two different stakeholders. One, the business. And it's weird to think about it in politics, but the business is a $6 billion industry, basically an ad campaign that lasts about a year and a half. It's continuously flowing. But anything I talk about today with Romney or Obama, you can picture Ford and Toyota or Apple and Microsoft. It's all the same. And then you can also think about the research angle, which is that it's not just one side is providing the efficiency that a good indicator provides to a business or a company, and the other side is thinking, well, what do we really learn about why things change and how things change over time, and thinking about it from the kind of the research angle as well, interested to both parties. And we have two main stakeholders, and I kind of think about four main kind of key goals when I describe an indicator or a forecast to somebody. And the four of them are going to be here. It's going to be making sure that it's relevant, timely, accurate, and cost-effective and scalable. These all seem like painfully obvious, and if this was a different talk, I can go into how many examples of how horrible we are in thinking about these main goals, whether or not it's relevant. You know, in elections, we generally tend to talk about the latest poll, which is just a raw data point that looks something like an expected vote share, which is not the probability of victory that most people care about. Timely, we don't make forecasts when they're most necessary. We make them when they're most convenient. Accurate, that's a tough one to describe for some people, but you know, people think about the simplest kind of mean absolute errors and types of things rather than thinking about how well something's calibrated and whether or not it's robust to describing the future or describing the past. And of course, scalable, cost-effective, which is what all of this machine learning, big data, everything is going to open up, is the ability to answer tons of new questions and tons of new domains. But of course, coming from academia, you know, if I spent $1 billion and made it infinitesimally, significantly significant, statistically significant, people are like, that's awesome, totally forgetting and not caring about the scalability, the practical implications. So I'll talk about it a little about today. This is some of the data which I generally deal with on a regular basis. And the challenge is thinking, you know, how do we put this together to make things that sing for people? And in the past, it's not that hard in some cases a little harder. But you know, you look at something like a GOP primary, this is kind of aggregated from polls and some fundamental data and a little bit from the prediction markets. And it shows this is the general support for candidates at any given time. You know, it bounced back and forth. And this is the probability of victory at any given time. This goes to this question of relevancy and thinking about what you need to do. These are all from kind of traditional data sources. And these paint very different pictures. This is what the news media focused in on more. This is what I think we should have been talking about a lot more because this is what was most relevant to most people. Romney was going to win the whole time. Seems meaningful. And when you start thinking about things like kind of how new data sets start playing into it, it's thinking about, well, in the past, it was very hard to kind of get timely updates on things because polling is done every few days. It takes a while. Prediction markets, social media data help you kind of construct things that say, so let's say we all started at the same point. So this is saying in the beginning of the debate, you start at 0. This is the movement of the likelihood of Obama winning the election as the 3 major debates moved. This granularity is extremely important to answering questions about the impact of events, and the timeliness is extremely important in people who are making investments or moving money around based off of how things are going. But since I have so little time, I'm not going to talk about all this stuff, which is kind of the standard stuff. I'm going to be talking about how we're facing the future and how things are going to change, and it's with online data and kind of experimental polling and predictions. And I'll start out by posing the challenge. The challenge is that the main data source for politics and a huge amount of market intelligence has been representative polling. Representative polling, you've got a random sample of a representative group of people. It used to be a very high amount of people you can contact and a high amount of people then responded. That is almost gone now. So you're down to less than 10% of people that you've randomly chosen to poll actually answer the poll. This cuts down the statistical benefit of the randomness. It also makes it increasingly expensive to do this. Representative polling basically is dominant because of the Literary Digest failure of 1936. Freaks people out. Literary Digest went and tried to just interview as many people as possible. They didn't do anything to correct for it, and they had a horribly terrible poll. They interviewed 2 million people out of 10 million people they tried to get. These are mainly car owners and subscribers to Literary Digest, and they were much more likely to be Republicans, and they predicted a Landon victory. Roosevelt won in a landslide. But times have changed since 1936, and there's new technology. Shocking, as that sounds. And it's increasingly cheap to get non-representative people. That took months for Literary Digest. I could do it in days to contact millions of people if I really needed to. And these are out of order for some reason. But we know that non-representative polls, if you can unleash the power of them, we know we can ask the right questions. We know we can get people quickly. We know it's going to be cost effective because it's pennies on the dollar compared to representative polling. The question is, can you make it accurate? That's the challenge. And then we're making that accurate, and we're trying to phase it by kind of 4 different things. We're hitting it on kind of incentivizing the right people to answer the polls, thinking about new questions, including graphical interfaces that can reveal new information from people, thinking about new ways to aggregate that data, and thinking about new incentive structures to get people to respond truthfully and meaningfully. And I'll give one example here. This is work that I did with Justin Wolfers, who's now at Michigan. And we basically said, well, maybe we can ask a different question. So we found examples 345 times. Same people, same time were asked, who are you going to vote for in an election? Who do you expect to win? When the polls pointed in different directions, when people expected someone that they didn't intend, 75% of the time, the expectation pointed to the winner, okay? So just thinking about that, and what we were able to do is then, so we went on to Xbox and we asked people who they expected to win their state, and 51 out of 51 states, including the District of Columbia, pointed in the correct direction. People expected the eventual winner in their state, okay? So that was a really simple way to just ask the right question, and you can start tackling that problem. And then we get some nice press for it because this is like a screenshot. I don't know how much an ad like that would cost, but that's pretty cool. Also, graphical interfaces, right? So we were like, can we get really complicated things maybe to get revealed, things that would be even harder than you would think normal poll that can actually do something. This was work with Dan Goldstein. We showed 100 digits between 1 and 10 to people that would come from 6 different distributions that you can see on top. And then when we aggregate up their responses, when we ask them to reveal the distribution they saw, using this new graphical interfaces we've been working with, we're getting results like this, which is not perfect, but people are actually kind of revealing that they really got the distribution. You can see a little skew in there, some kurtosis. I mean, they're hitting all the key moments, right? So that's kind of cool. But let me jump back into kind of an even bigger project, which is this full breadth of this Xbox project. We interviewed 350,000 users. They took 750,000 polls, which are 3 to 5 questions long, over the last 45 days of the election. And we had a lot of repeat users. So we had massive quantity, and we had massive panel. We had 5,000 users who came back at least 15 times or more in 45 days to answer questions from us. And so we could see how they moved. Standard polling basically has this idea that you just let the data flow through. You chop off a chunk of the people who were not likely voters, or if you think about this in terms of market, not likely shoppers, whatever it is, drop them off, just say, what did the poll results say? What we said is that we want to use new tools in order to allow different cells to inform each other. So essentially, we broke everyone down into their demographics. We broke down into 6,500 different cells of combinations of demographics. And we said, what's the likelihood of any cell polling for any given candidate on any given day? And then post-stratifying that over a set of what we assumed the likely voters to be, we used something very simple, which was the 2008 exit polls. We did the same thing with 2012 exit polls. You get the same thing, but we wanted to show that it was robust to simple choices. Key thing here, number one is that we have a panel, which I'll talk about in a second. But number two is that we get 20,000 people a day. So even though we had very little amount of over 65-year-old women, we still had 4 times as many than, say, like Gallup gets on a regular basis. And what we're able to do, and you're not going to be able to see this, but I'm comparing our results to pollsters' results. These are kind of main poll aggregating things on a state-by-state level. We show a lot of robustness. Kind of a little cleaner thing to show is that what I broke down here is that on the x-axis, this is our estimate for any combination of demographics to, so like say, over 65-year-old women or white males in a certain age group, whatever it is. And this is their actual two-party vote share. So this is breaking down all these subgroups. And we're able to show that our estimates were actually pretty on par. Sitting on that 45-degree line is the goal. And so step one is to say we're seeing something that looks on par. And just remember, there's no ground truth here. So it's a tricky question in the sense that we don't actually know baseline levels of support. We don't actually know the likelihood of Obama winning the election on October 2nd or October 10th. All we know is what happened on Election Day. But similar to the main stuff, that's good. And then what we see here is on the left here, this is the percentage of Democrats after accounting for demographics who showed up in our polls. And this is how our top line poll moved. And this was very similar to Gallup, Pew, and everything else. And we sat there and we said, these look really similar. These look shockingly similar. And from that, we were able to determine things like, well, it's actually this partisan non-response that's driving a huge amount of this movement on these polls that are making all of this investment decisions, that are making all this noise. Essentially, what's happening is Democrats were really sad after the first debate and were like, I'm not going to answer a poll. So if you assume that a polling company was looking for like a white male in a certain age group or whatever like that, what they end up is just being slightly more likely that a Republican is going to answer on the days where the Democrats are sad, and then slightly more likely that a Democrat's going to answer the days that, and what happens is if you kind of look at also the movement between that we see. This is the panel aspect comes in. We get to see about where people are actually switching. We're able to determine, and it's so rare you get to use pie charts in academic talks, so I was pretty stoked about this. But I just want to make this really clear that if you looked at the total shift that happened during an election cycle, about 2/3 of it is being driven by people not answering the polls, which is very loosely correlated with not likely to vote, but it's actually very little. And that 1/3 that's a shift in support, actually the vast majority of it is a shift from like other to a major candidate, or between a major candidate and other. Essentially, the kind of these time shifts that aren't that meaningful is this tiny portion of a tiny portion. They're actually people moving between candidates. The thing we think of when we see these gigantic shifts, and I'm out of time, through convention stuff. And so I'll leave it at one more thing. And the real challenge then comes down to is, can we start applying this to this another set of polls, which I really care about, which is social media data and online data, which I look at as saying, I have a poll. I got a couple 100 million respondents a day. We sort of know their demographics. We sort of know the question. Can we start applying these same techniques to start breaking down what is unrepresentative data that moves around, has all these unique things to actually answer questions that we care about? So thank you.
Mary.
Yeah, so so the question is about artisanal data and polling and big data, and the answer really comes down to is that most of the stuff I showed you and most of the stuff we're using really is, I think, falls under the idea of artisanal data in the sense that it's very small data sets specifically collected to fill answers, because you look at these massive data sets and you're not sure what the question is, you're not sure who's on it, and the amount of work to possibly answer some of the questions like predictions would be devastating compared to actually going out there and directly asking people to answer the question you care about. That's not to say, though, that we don't want to kind of break that key, open that up, and if we could do that, then you have this cost-effective way to answer all sorts of questions in all sorts of domains. But until we get to that point, we still need to go out and actively collect small amounts of data that very efficiently answer the questions we care about.
All right, so for our final speaker, we have Eric Horowitz. Eric is one of our own at Microsoft Research. It's really a pleasure to have Eric here because he's been one of the people throughout his career who's really been making fundamental contributions toward, pushing us toward AI, looking at decision-making under certainty and, fundamental reasoning questions. So thanks for
So I thought I'd change gears and focal length here a bit and answer the question that Sham asked me to think about, which was, in 15 minutes or less, what has progress been in machine learning and what are future directions? So it's quite an interesting challenge. I thought I'd start by reflecting back about the last 30 years, which I found a very, very interesting and exciting time. In particular, it's a time when the computational lens, the lens of actually, or the goal of implementing procedures and algorithms and representations has increased our learning about probability theoretically. The foundations of representing probability distributions, for example. And a lot of this work was done by people pursuing machine intelligence. What does it mean to reason under uncertainty, to represent knowledge? What does it mean to reason tractably and to learn from data and to do science? And one of the representational advances, and I think representation is a theme for moving forward into the future as well, has been moving to computational graph theoretic models of probability, in particular graphical models. Directed graphs, for example, capturing distinctions one cares about in the world and the dependencies and representing them, and coming up with tractable procedures. In fact, Redmond lab result about a decade ago proved some of these, even though greedy search and greedy in nature were optimal. They would find the optimal way to express, or the optimal graphical model to express a probability distribution, and allows us to build models that can actually be used to diagnose illness, for example, in healthcare from large sets of data. Moving ahead from directed models to undirected graphs, another shift of representation, which has been very interesting for the field, and to link back to Peter Winkler's talk, these representations, including Markov random fields and conditional random fields, are very akin to icing models in statistical physics. And from my point of view, these models have actually, representations have actually given us a little bit of magic that's jumped out. The ability to represent simultaneously and jointly different kinds of information. For example, taking a personal photo album and folding in events and time and locations, and all of a sudden to triple the accuracy with representing individual faces in the whole library, for example. And that these kinds of undirected graphs and methods were used in some innovations at our Cambridge lab in, for example, segmenting out background from foreground. What was there, a street versus a road, road or sky or building. And this kind of methodology was actually the ancestor of some of the work we've heard about it with the Connect work, changing consumer expectations as to what computation might be doing moving forward. Representation is also very interesting, and it's gotten some new attention in thinking about deep neural networks. These are basically stacked representations. The models aren't very new. However, in the old days, in the late 1980s, in the last wave of neural net interest and excitement, we didn't have the kind of data to really blow across the high dimensionality of these models, these large parameter spaces. And now when we have that data, we're seeing surprising gains, for example, in the accuracy with which we understand a workload called the switchboard data set of conversations in the wild on low bandwidth phones. These methods also discover their own features, which has been an interesting area of study, to understand how these systems with relatively simple algorithms, backprop and optimization, can discover higher and higher levels of abstraction of how we look at the world and combine information about the world. And of course, what's also another interesting challenge right now is, given the large-scale nature of some of these learning processes, even though the algorithms are straightforward, there are some interesting systems innovations going on right now with implementation. This is actually a competitive space among corporations, and some people view this kind of race, even using this methodology right now, as a modern-day gold rush for talent, and also for the latest accuracy results in neck and neck, for example, on who's going to sell more phones and so on. So moving forward, and this obviously doesn't have a very long transmission length, you have to say, but stay near the antenna here. Another theme I think we'll be seeing more and more moving to the future is not just worrying about prediction, but thinking about decisions, getting to the utility structure of our problems. This is where the rubber meets the road in intelligent systems. And so going from data to predictions to decisions is a fabulous way to think about our implementations, because when you think about the learning problem, about what we want to do, the utility structure actually has implications for the very first stages of this chain. What data do we get? How much is it worth? Where should we put our computational effort, for example, even in a deep neural network system, to put the effort where it counts for the utility structure of an environment? With active learning, and we've seen such little work in this space, given how promising this is, we ask, what additional data, given what I have so far, should I collect for goal X? How much is it worth? In an actual live situation with users working with computing systems, a stream of evidence comes flying through the system, and sometimes we need to understand and interpret state, which is an effortful task of labeling. And value of information computations can tell us the value of a probe or a label versus its cost. And that could be very critical in thinking through how to limit, for example, human effort and attention, for example, in annotating a personal photo library. I need to know about these pictures. Tell me about those two, nothing else. I'm okay with everything else. Or I need to know about this meeting. Was this meeting an important meeting for you? Or in real time, are you busy now? I know this is interrupting you, but if you tell me about now, I'll be able to do much better in the future. Value of information computations can power that work. Thinking about utility and decision making comes to mind about a project that was a collaboration between the New England lab and the Redmond lab early on in this lab's history, when two postdocs, Mohsen Bayatsi and Mark Raverman, approached me about healthcare work and doing machine learning in healthcare. And what you see here is a screen of the form being used throughout the world now in a live system that's predicting for patients, so you discharge them, the probability they'll bounce back to the hospital in a certain period of time. Now, it's really great as we speak, that these systems are actually learning locally and training up models and predicting. But to have hospitals send us the dollars they're saving, and this is like actual data from a hospital coming in, readmissions going down and so on. But one thing and this will frame the next version, the next stage of this project, they're making decisions about, well, if the score is greater than 25, I will do this intervention. I will take this action and see what happens. In reality, we can look at a disease process like heart failure, for example, look at the utility structure of what you would do and how much it would cost and the probability it would reduce the readmissions rate, and generate over uncertain parameters the expected value of putting a live decision system in a hospital system. This utility structure helps us understand the whole end-to-end value proposition, you might say. Another direction and a theme for future work, looking back and looking forward, is temporal reasoning and temporality, reasoning about space and time. A lot's been done in this space, but it's always been viewed as a combinatorial, explosive dimension to get into. Most machine learning really reasons about the here and now, classifying X with some static atemporal features. And time is very, very powerful. An elegant and simple, yet sophisticated in its thinking for the foundations methodology for temporal reasoning beat out other methods in a showdown to basically come up with the best way to prefetch content and pre-launch applications in Windows 8.1 in an MSR Windows collaboration, and that's running now. And it makes it such that when you touch any tile, it'll be up instantly with all its data it needs 85% of the time. Temporal reasoning is also important in search. This shows what happened after the Fukushima tsunami with certain kinds of pages and their popularity on the web. This is very useful for understanding how to rank over time with temporal functions. And back to healthcare again, in a collaboration we're doing at Redmond with, I have to say, MIT again, with Don Gutag's team. We're looking at predicting hospital-acquired infections in hospitals. Will they happen within 48 hours? Hospital-acquired infections are in the top 10 killers in the United States for all causes of death. And we're predicting quite well, in many cases, that this patient here is at risk of becoming ill. By moving into a time domain, we're looking at infection as being a time function of susceptibility and exposure. We end up in a situation where we can enhance the power of our methods. So a patient usually goes through a number of different rooms in a hospital. We can compute over time how many others were infected in different wings of the hospital. And based on that, bring up our accuracy rates significantly by temporal reasoning. It's a hard, challenging area, but a useful area for innovation. Causality is another really hot topic. Here are some distinctions that the machine learning procedures said were important for predicting hospital-acquired infection. The unit, who's the doctor, some medications, they're all kind of surprising. You have to be very cautious because it turns out in this case, this is the attending in the ICU. That's all the hard cases. Causality is critical, and it's a really interesting area. Lots of innovations there in the graphical modeling space of late, few of which have been applied in the real world yet. And causality applies in many places. This is a chart from our Silicon Valley lab, Moises Goldschmidt and others, looking at data centers, trying to figure out what's the actual root cause of the slowdown in this data center. We reason about the same methods in the hospital as in our data centers today. Now, I'm going to just highlight two areas before I end today that I think talk to this lab in particular, because I was talking to Christian and Jennifer early on about social computing and theory, and interesting, wow, let's do it. And this gets into the world of people and machines. For learning and interaction, for example, some work that Adam Kalai did several years ago, the basic idea was use an active learning algorithm to ask people about similarity, to structure or triage their effort, and then build a kernel or a whole lattice of similarities that can be used in a live system that actually runs based on the human input. So people are playing an important role in building systems, and how to triage their attention is going to be critical. In another system in the Redmond lab, users play a game trying to get misdiagnoses onto this line to make the classifier better, moving around a wheel that weights different classifiers, multi-classifier setting, and partitioning. And based on the data coming from this, we can build, watching how humans do machine learning, build a better machine learning procedure that can see further out than the myopia of some of the procedures that exist today. And thinking about people and machines, this whole area of complementary computing, as machines get more and more powerful, can do more and more things, what's the role of humans? And how do we work together in a collaboration? So this is some fun work I'm pointing out here using the Da Vinci robotic system, which is typically robotic because it's more of a kind of a transmission for surgeons in terms of being a direct manipulation system. But Greg Hager's group at Johns Hopkins has built a system that basically watches what's going on, stays in manual mode, goes to automated mode, and starts taking over the actual suturing, for example, or other surgical interventions in a mixed initiative back and forth. But speaking of this kind of thing in the intellectual space, we can sort of, this is a project at MSR, Redmond, take machine perception and human perception together and do citizen science with a tool that understands how to best use imagery done with machine vision and human effort to tag, for example, different kinds of galaxies. We can half the amount of people needed, we show, and get more accurate by ideally fusing and routing tasks. And I'll end by talking a little bit about another interesting trend and I think a direction for machine learning in the social computing world. And this was alluded to by the last couple of talks. Social behavioral data leverage for people and society. So this shows is highlighting some work we've done in the Redmond lab, led by Munmundu Tuturi. What you see here are characterizations of Twitter feeds, and we have 5 characterizations here looking at the volume, replies, affect, activation, and first person being mentioned. This red line is when hundreds of people had a birth and said, I just had a baby girl, isn't this great? And we have a methodology for identifying these and then lining up all these people, then using some well-known tools coming out of places like UT Austin for capturing affect over time, and watching what happens when this major life event occurs in the lives of women. We know that 50% of women, it's underreported, suffer from postpartum depression and blues. This was even in the news lately with a car in DC area, an unfortunate tragic event. But what we found is we can actually not only detect severe changes in about 10 to 15% of women, we can predict it in advance of it happening, which is interesting implications ethically and also towards public health. This also, we also consider aspects of the social graph as an evidence set on this. And just a couple more examples here. This is just being submitted this week. Similar work looking at identifying in large-scale search logs. This was with Michael Paul from Johns Hopkins, an intern in our team, that someone has had a breast cancer diagnosis, and what happens at that point, using classifiers to discover these people, as well as the timing, 2 different kinds of classifiers, and watch what happens with questions about chemotherapy and radiation at the point of diagnosis for thousands of women, we believe, who had just had their breast cancer diagnosis. In the news this year also was using large-scale search logs to reason about drug interactions, people searching on one drug and then another, and then terms that reflect symptomatology. Not just showing this for one combination of drugs, but looking at 62 sets of true positives and true negatives, and characterizing the web, the noisy sensor the web can be, making it a more reliable sensor for public health in this space. And I'm just going to be a couple more examples using really exotic data, like using 70 years of New York Times headlines and other data from the web to compute and discover that a strong drought followed by a flood in certain regions of the world for their properties is an indicator for a high likelihood of cholera. That's gotten Gates involved and so on. So I'll stop there by just my last slide here before Kristen stops me is saying that the dream of machine intelligence really is driving a lot of this work, even though along the way we're doing all sorts of fun things. And I just want to make a comment that that work in both the fabric and the foundations, as well as in the integration of these components, I think will actually lead us to the initial dream that led to some of these initial advances we see that enable some of these applications today. So thanks a lot.
Okay, thank you, Eric. I think I think we will have to put the questions for the lunch break.
Great.
But let's also thank Sham and all the speakers of this session for this beautiful session.